What kinds of functions can we just look at and see that they're continuous? Well, one of them is our polynomial functions that we talked about. Polynomials are continuous for all x values, from minus infinity to plus infinity. This means things like straight lines, parabolas, cubic functions, quartic functions, all of those can be drawn without lifting up your marker or your pencil. So they're continuous everywhere. A rational function, remember, those are the things that have the vertical and the horizontal asymptotes. And they're going to be continuous everywhere as long as the denominator is not equal to 0, because remember, that's what gives us the vertical asymptotes. If you find where your vertical asymptotes are by setting the bottom equal to 0, that breaks the graph up into pieces, and along those pieces, we know that the function is continuous. So in this case, we had one vertical asymptote, and that means we're continuous on the left-hand side of the vertical asymptote and on the right-hand side of the vertical asymptote. Root functions, things like square root of ax plus b, well, they're continuous wherever anything underneath the square root comes out to be positive or 0. That's going to happen starting at some point and then moving to the right. So everything to the right of this point is going to be continuous because I can draw it without lifting up my pencil. Exponential functions, they're continuous everywhere because they extend infinitely far to the left and the right, and I can draw it without lifting up my marker here. Logarithmic functions, remember, logarithms are only defined for positive values. I'm going to be able, remember there's a vertical asymptote here, and everything to the right of that vertical asymptote, which are my positive values, I'm going to be able to draw this without lifting up my marker here. So for values x greater than 0. One of the places that we'll run into continuity is when we're working with functions and we want to know if they're discontinuous, if they have any big gaps in them. Because sometimes if there's a big gap in a demand function, that tells me something about this particular manufacturer. Maybe they're discounting things a bit. Here I have a piecewise function. By that I mean it's defined in 3 different pieces. If you're using x values that are less than 2, it's defined by the formula 1. If you're using x values between 2 and 4, including 2 and 4, it's defined by the linear function x plus 3. If you're working with x values that are greater than 4, then it's defined by the constant function. You need to be a little bit careful. If I ask you to find f of 10, where does that fall? Well, 10 is an x value that's greater than 4, so that means the output is defined by the third part of the function, so this is just 7. If I say, what is f of 3? Well, 3 falls between 2 and 4, so that means I need to put it into the second piece of the formula. 3 plus 3 is equal to 6. Notice that at no point when I have an input will I put it into all 3 pieces simultaneously. If you give me a value like f of 0, I pick which piece it fits into, so 0 is less than 2, and then I use the corresponding formula to tell me what the output is, in this case 1. So the question lies is, 1 is just a constant function, that's just a horizontal line. X plus 3 is a straight line with a slope of 1 and an intercept of 3. And 7 is another constant function, that's a horizontal line. Each one of those individually is a continuous function, but at 2 and at 4, do they all connect up? If they do, well then that means it's continuous. If they don't, well then we have some points of discontinuity. Each one of the pieces are continuous over their individual domains that we've just talked about. But what we have to find out is at the point 2 and at the point 4, do they meet our definitions of continuity at a point? Let's look at x equals 2 and x equals 4, and we'll do the limit as x approaches 2 of f of x, and then we'll check to make sure it's equal to f of 2. We'll do the limit as x approaches 4 of f of x and make sure that that's equal to f of 4. This is just that definition, part 3 of the definition of being continuous at a point. So let's do each one of these at a time. To be able to do the limit as x approaches 2, I have to do it from the left and also from the right. So if x is approaching 2 from the left, well, that means we're in this piece right here, and the function there is 1. So the limit as x approaches 2 from the left of 1 is just 1. If I'm trying to find it from the right-hand side, well, now I'm in the piece that goes from 2 to 4, so now I'm taking the limit of x plus 3 as x approaches 2, and this is just a polynomial, so I can plug 2 into it. 2 plus 3 is 5. So my two one-sided limits do not match up. What that means is that if I try and do the limit as x approaches 2 from both sides, it is not going to match up. So the limit does not exist, so this is not continuous automatically. We can't even go ahead and go to the last part and figure out what f of 2 is, because the limit to begin with is not continuous. So there's some kind of a gap in this function. What about at 4? We'll do the same thing. We'll look from the left and from the right. On the left-hand side of 4, the formula is x plus 3. On the right-hand side, it's just 7. And if I do the limit of x plus 3 as x approaches 4, I get 7. The limit of 7 as x approaches 4, that's just a constant function, so it's 7. So in this case, the limits match up. And when I do f of 4, I also get 7. So all of these things match up, so I know this is continuous at x equals 4. If I were to go ahead and graph this, I would see at x approaches 4, we're getting closer and closer to 7, either from the right or from the left, and the point there fills it in. But remember, when we did approaching 2, from the left, we were getting 1. From the right, we were getting 5. And in fact, if we had plugged the number in, we would have gotten 5. But notice, things don't match up. They're not equal because the limit did not exist. So there's a discontinuity at 2, and it's continuous at 4. Let's see how this would come up in one of these pricing schemes like I was talking about before. A company charges $1.20 per pound for a certain fertilizer on all orders not over 100 pounds, and $1 per pound for orders that are over 100 pounds. So if you order more than 100 pounds, you get a discount of 20 cents here. Let f of x represent the cost for buying x pounds of fertilizer, and what I want to know is f of x continuous. So let's start by defining the function f of x, and this function is going to have two different formulas depending on whether you purchase more or less than 100 pounds. If your order is for less than 100 pounds or equal to 100 pounds, you're going to take how many pounds times the cost per pound, which was $1.20. So your formula is going to be f of x equals 1.2x. For more than 100 pounds, you're going to take the number of pounds and you're going to go ahead and multiply it by the dollars per pound, so you're going to get 1x. So in fact, we really have two different formulas here. So this is a piecewise function. It has two pieces to it. One of them is 1.2x. If your x's fall between 0 and less than or equal to 100, and 1x if x is greater than 100. What we want to know is at 100, do these two pieces connect up? So I've gone ahead and written down my piecewise function. And now we need to decide if it's continuous. We need to find our limit as x approaches 100 of that function. We'll do the two-sided limits there to see if they match up. And if they do match up, we'll see if the point at 100 fills in where they match up. We'll write down our function and we'll do the limit as x approaches 100 from the left. And if we're doing that, we're in the 1.2x formula. As x approaches 100 from the left, well, this is just a polynomial, a linear function. Plug 100 in, we get 120. Let's approach it from the right-hand side. Now we're in the other piece, so now we're taking the limit of 1x as x approaches 100. And again, this is just a linear function. We'll plug 100 into it, we get 100. From one side we get 120. From the other side we get 100. These two do not match up, so we know right away that the limit does not exist. We don't even have to go ahead and find f of 100 because we already know we can't find the limit. We know things don't match up. F of 100 was actually equal to 120. So now we know that this function is discontinuous at 100. If we were to go ahead and graph it, what you would see is that as we move along the left-hand side, we go up to 120, and there's f of 100, it's 120. But from the right-hand side, we're getting closer and closer to 100. So here's that jump in the cost that we're talking about. And so if you were going to purchase something about right here, you'd probably just want to up your order because if you go a little over 100 pounds, you'd actually be paying less. As long as you have the storage for that, you'd be in good shape.